Welcome to lecture 2. In the first lecture, we saw an overview of the course, the objectives of the course, what we will do during the course. Then we recapped some of the important concepts that you should have learned in the theory of computation course, such as what are Turing machines, what's the configuration, how does the Turing machine operate, right? And then the O notation and so on. Towards the end of the lecture, we defined the complexity class DTIME TN, right? Which is a set of all problems, all computational problems or languages that can be decided in time order Tn, right? So palindrome can be decided in order n, so it is part of palindrome is contained in DTIME n, and the D stands for deterministic time. If you look at SIPSR, they just use the notation time Tn, but just to emphasize the fact that it is deterministic, I am using DTIME. So we will very soon see non-deterministic complexity classes, so like n time Tn. So that is the reason for distinguishing between deterministic and non-deterministic. So deterministic means at every step, given a current configuration, there is only one subsequent step that the Turing machine can take. Non-deterministic means instead of 1 it could be 0 or 1 or 2 or anything more than 2 also, right? So there could be multiple choices available at any given instance. Anyway, right now we will just see deterministic. It is simple, so let us move ahead with that. Right, so this is something that we don't need. And it could be multi-tape, so the way we defined it. So there is a small difference between multi-tape and single tape machine. So anything that can be done by a multi-tape machine can also be done by a single tape machine, but it takes a bit more time. Since that is not the main scope of this, that's not really in the main scope of our course, and since we are constrained by time and I want to cover other stuff, I will not get into that. So we will use multi-tape Turing machines, right? And we will use multi-tape Turing machines, okay? And another definition, a complexity class. It's an important complexity class P. Okay, P is a set of all DTIME n power k. So n here stands for the input size. K is the constant, so you can consider it as k equal to 1 to infinity. So you can consider it as integers. So n DTIME n union DTIME n squared, DTIME n cube, and so on, right? So anything that can be completed in a in n power k for where k is any constant number like n power 100, any problem that can be decided in time n squared or n cubed or even n power 100 or even n power million will be considered to be part of P, right? So it doesn't matter what the k is as long as it's a constant. So n power 100 is okay, n power 1000 is okay, n power 1 is okay, 2 is okay, anything is okay, except the most important thing is that the exponent of n should be a constant. So you cannot have n power log n, for instance. So even let's say n is like 1000 or million or whatever, then log n is a very small number. So log of million is something like 20, I suppose, right? And log of 20 will be something like 4 or 5. So it's a small number when you take log 2 times, so this becomes a small number, but this is not a constant because it is log n, it's a function of n. But what is allowed is any constant. It could be huge constant, doesn't matter. So this is the class P. P stands for polynomial time computable. So polynomial means anything of the form n power k, where k is a constant. So n power 1, n power 2, n power 3, anything, n power 100, n power 1000, right? All of these are polynomial time. All of these are polynomial. So this is P stands for polynomial time solvable. So, or polynomial time, maybe I will say decidable. So we have decision problems that we are looking at, as I said in the last lecture, because most of the time we will be asked to decide whether the given input has a certain property, like whether this graph is connected, whether this number is odd, or whether this number is a prime, right? So can the given computational problem is that decidable in polynomial time, right? So these or the class of problems that are decidable in polynomial time are P. Okay, right. So now why is P an important, or what is significance of P, right? So there are some minor significance, and after that I will say some history. So some important significance, sorry, it's a bit messy. Of the class P. P stands for polynomial time decidable. So one is that it is robust, which by that I mean it's independent of the model of computation, exact model of computation. So as I said, a multi-tape Turing machine, anything that can be done using a multi-tape Turing machine can be decided by a single tape Turing machine, but that involves a small blow up of the cost. So for instance, the running time squares. So if you take a problem that takes n cubed time in multi-tape Turing machine, we know that it can be done using a single tape Turing machine in n power 6 time, so n cubed square time. So we already saw palindrome that takes n order n time using a 2 tape Turing machine. So it could have been any tape Turing machine, but we used only 2 tapes. And you can try using single tape Turing machine, you will need n squared time, right? So, but then both n squared, n cubed, or n squared, or n cubed, n power 6, all of them are polynomials, right? They are all n with a constant power on the top. So it doesn't matter which model, single tape, multi tape, or even there are other differences that we could get into. But whatever model you take, as long as it fits within the standard Turing machine framework, right? The definition of the class polynomial time remains the same. Whereas if you take the class DTIME n, if we say it is single tape, multi-tape Turing machine, then palindrome will be in the class. Whereas if we don't allow multi-tape Turing machines, if it has to be single tape Turing machines, then palindrome cannot be in the class DTIME n, because using a single tape and order n time, you cannot decide palindrome. So that way it is not a robust class, DTIME n, for instance, whereas P is robust that way, right? That is one point. And the most important point about P, or most important significance about P, is the notion of efficiency, right? So one can ask what constitutes an efficient algorithm, and the most common answer that you will get, or the most widely accepted answer, is the class P constitutes the class of efficient algorithms, or the class P constitutes the class of problems that have efficient algorithms, right? Because so you may ask, like, n power 100, is that really efficient? Because n power 100 can be huge even for a small n, right? But it is still polynomial, and the point is that when you contrast with what is called an exponential time algorithm, right? So for instance, something like 2 power n, you will see that n power 100 is slower growing than 2 power n, right? So for small n, maybe let's say n equal to 10 or something, 2 power n will be smaller than n power 100, but let's say for n greater than 100, you can take n equal to 100, or maybe n equal to 1000 or something, then you will see that beyond a point, 2 power n becomes greater than n power 100, and after that it continues to be bigger, right? Because this grows much faster because it's exponential. So polynomial time functions are slower growing than exponential, and this is one reason why it is considered efficient. Another reason is that for most problems of interest, right? So you can create artificial problems that take a long time. That is not of interest. What we are interested in is problems that are of real significance, practical importance, right? For these type of problems, usually you don't get such running times. So usually the running times are like n cubed, n power 4, something. Most of the problems that are of significance to us, right? The running time will be n cubed, n power 4, n power, like not even n power 4. Mostly most of the algorithms that you will see in the algorithms class, n cubed, n squared, n log n, n squared log n, things like that. Right. So even so there are some problems for which people struggle to find algorithms, efficient algorithms. Maybe the first attempt at an efficient algorithm yielded n power 10 or n power 20 or something. Very soon what is commonly seen is that somebody else brings the n power 20 algorithm to n power 10 algorithm, somebody else optimizes it further and gets an n power 5, and then like that it gets improved, and usually the best algorithm is usually something that is practical, right? So these are the two. So this is, maybe I'll just note this is a different point. So polynomial versus exponential, right? So this is another point. The first point is that it is robust. It is independent of what model you have, what exact model you have. Second is that it is commonly considered as the class of efficient problems for which there are efficient algorithms. And three is the fact that this is polynomial and we have to contrast it with the exponential time, right? And again, this again P means P is a union of D time, so P actually is deterministic polynomial time. Okay, so we'll soon see NP, which is non-deterministic polynomial time. So P is actually deterministic polynomial time. Maybe I'll change the color. Deterministic polynomial time. So maybe I'll just say a bit of history at this point. All right. So as so this most of the area of computational complexity developed starting from the 1970s, early 1970s, when the theory of NP completeness was put forth by Steve Cook and independently Levin in the 72, 73 or so on. And then people started working on it as a research area, and then continued to make progress in the 80s and 90s, right? And even now it's a very exciting field of research. But around 8 to 10 years back, so this paper was first, I think, some preprint or some published in 1963. Okay, so this is the excerpt from a paper. The paper title is interesting. It's called Paths, Trees and Flowers. It takes a particular computational problem and it tries to solve it. So I don't want to get into what problem it is. If you're interested, you could look up the paper called Paths, Trees and Flowers. It was published in 1963. The author is Jack Edmonds, right? Or we could you could email me, or we could discuss in one of the meeting sessions about the paper itself. But why this paper was interesting is that about 10 years prior to the development of the theory of NP completeness, this paper asked some very interesting questions, right? So okay, the introduction is about the specific problem, and so I only attached some excerpts, right? I skipped most of the introduction and then gone on to section 2, in which the author goes into what he calls digression, right? So he asks, what is an efficient algorithm, right? An explanation is due on the use of the words efficient algorithm, right? And he says that what he presents is a pseudocode as a conceptual, not even pseudocode, a conceptual description, maybe a description in English, and not something that can be readily accepted by a computer, right? It needs to be written into, it needs to be programmed. It's not a full-fledged computer program. And he says, without getting into the details of what the full-fledged program is, I think this is efficient. Like he has to sell his algorithm, right? He's proposing an algorithm for a problem. He says, so now he has to say why his algorithm is superior to the other existing algorithm. So then he has to say that mine is efficient. Now, what does efficiency mean? So till that point, it had not been studied. So he says any problem has an obviously finite algorithm, right? So which means, by that he means a brute force approach, right? So you want to do something, you can do a brute force thing, but that obviously finite algorithm increases in difficulty exponentially with the size of the graph. So in his case, it's a graph, right? So exponentially is, again, I mentioned, so this is exponential and this is polynomial, right? So the brute force algorithm, or what he calls the obvious finite algorithm, increases in difficulty exponentially with the size of the graph. And it's not clear whether there is an algorithm that does much better than that, right? And he says, if you go, you can go through this entirely. He says the mathematical significance of this paper is largely on the assumption that these two preceding sentences are math. Okay, so it is by no means obvious whether there exists an algorithm whose difficulty increases only algebraically within the size of the graph, with the size of the graph. So algebraically is another word for polynomially, right? Even though it's not so commonly used now. So by algebraically he means polynomial. So he knows there is an obvious finite algorithm which runs in exponential time. He's asking whether there is a polynomial algorithm, and then he goes on to explain why algebraic or polynomial time algorithm is better, and he goes into a bit of further discussion. So for the full details, you can download his paper. Paper is available online. The title is Paths, Trees and Flowers. So if you just type Paths, Trees and Flowers by Jack Edmonds in Google, you'll find a link to the PDF. You can read the full section too. It is about him asking what is efficient, what is not efficient, why is this efficient, and then defines running time and so on. So there are some other details to it. But what I want to emphasize here is that around 10 years prior to the development of NP completeness, this person, Jack Edmonds, asked what is efficient, and he says his algorithm is polynomial time and efficient, right? So so this is interesting that somebody was able to kind of foresee that or see that exponential is bad and polynomial time is good. And the later development of the theory of NP completeness kind of showed that this is the case, right? So again, polynomial, so anything n power k, just to summarize, polynomial means anything that can run in order n power k, where k is any integer. Exponential, we will not use it now. Order k power n, where k is some constant, right? So this k power n grows much faster. So you can try for small k's, like n power k will grow much faster than k power n. Even the k's need not be the same. For whatever k that you pick, you can check out that k power n grows much faster than n power k. So it may be small for small values of n, but as n so fix k or fix k1 here, and maybe you fix a k1 here and fix a k2 here. Whatever k1 and k2 you fix, if you increase n, after a point the exponential function will grow more than the polynomial function. So now I will go some and show some examples of polynomial time algorithm or polynomial time problems in P. So one is connected, the set of all connected graphs. So you could have a graph like this, right? Right? Or you could have a graph like this. So the difference between the graph in red and the graph in blue is that the graph in red does not have, it is not connected. So you cannot go from the leftmost vertex to the rightmost vertex using edges, because there are two parts that do not have any connectivity. Whereas the picture here, the blue, you can go from anywhere to anywhere by traversing the edges of the graph. So this problem of given a graph deciding whether it is connected, this problem is in P, has a polynomial time decider. So how? You may have heard of the traversal algorithms, depth first search or breadth first search. To check whether a graph is connected, all you have to do is run DFS or BFS, right? So you can run DFS or BFS. Both of them take order n plus m time, right? Where if the graph is given as a adjacency list, so let's assume that, and where m is the number of edges and n is the number of vertices. So the number of edges is at most n squared, right? Any undirected graph or any directed graph also, it's n squared edges. So this is polynomial time. So the problem connected or the language connected is in P, right? Maybe another problem. Given matrices or n by n matrices A and B, does the matrix A multiplied by B contain, let's say, 1 as an entry? So does the matrix, the product of AB, right, does it contain 1 as an entry? So this is another computational problem. So again, you could just multiply the matrices and then check whether it has a 1 as an entry. So this is also in P. Right, so I am not going into detail, you can work that out. And maybe another problem, 3 colorable. As I already mentioned, given a graph, can it be colored using 3 colors, so that no all the edges have distinct colors and on their endpoints. Sorry, I am just have distinct colors on their endpoints. So this is the 3 colorable problem. This is a problem for which even now we do not know if there is an efficient algorithm. Whereas if you take 2 colorable, we know it is polynomial time solvable. I leave it to you to think. So just like this 3 colorable, we can define 2 colorable, and 2 colorable is actually in P, and this is unknown or not known if it is in P. Right, and there are other problems. I can go on and on. There are so many computational problems. So anything that you can think of, there are so many examples, right? So these are some examples. Just to summarize what we have seen so far, We have seen the computational, the complexity class DTIME and deterministic time Tn or order Tn, and P is a deterministic polynomial time complexity class, and I explained the significance of this complexity class. It is robust. It is the class of all computational problems that have an efficient algorithm, right? And we saw some examples, right? And maybe I'll just say one or two more examples and then conclude. So, sorry, I'll just use the same color scheme. So, prime given an n-digit number, n-digit or n-bit number, let's say capital N, decide if n is prime. This is also in P. Okay. So this is another problem that is known to be in P. And you can define other problems as well. So this is the class deterministic polynomial time. In the next lecture, we will see non-deterministic polynomial time, how that relates to deterministic polynomial time, and I will explain the P versus NP question as well. Okay, yeah, thank you.